All right, so let me start by saying what the goal is for today. So the goal for this talk is to do two things. So the first thing I'll do, which will probably take somewhat more than half of the time, is to discuss the classification of vector bundles on a Farb-Fontaine curve. This topic will be used, I think, in both of the next two lectures, so this is why we changed the order around, so that I can do this first. And then with whatever time I have remaining, I want us to give a sort of an overview of the relative version of this story. So there's a notion of a relative Farb-Fontaine curve, which is a thing that occurs if you want to study moduli of vector bundles on the Farb-Fontaine curve, which if you think about classical algebraic geometry, moduli spaces of vector bundles play an important role. So, and this will also tie into my talk at in the conference next week. So that's sort of that's a good place to end this series. So first, let me quickly recall what happened last time. So I defined out of a perfectoid field of characteristic P, which I'll continue to call F. So I defined two closely related spaces, the schematic and adic Farb-Fontaine curves. So the first thing I did was I described this thing which I called XFN, which you'll recall was the Frobenius quotient of something called YF. So YF where YF was SPA of ANF with this sort of topology defined by, so this is with the P comma var pi adic topology. And then I took out the zero locus of, the vanishing locus of P and of bracket var pi. So I took out all the Frobenius fixed points, so now I have a free action of Frobenius. I divided by that to get the adic Farb-Fontaine curve. And then I defined a schematic construction, which was, this was the proj of the graded ring PF, where the nth graded component was the sections of this vector bundle O of n, this line bundle that I defined on XFN, right? O of n was defined by taking the trivial bundle up here and giving it the phi action where that carries some generator to p to the minus n times itself. So that choice of the minus is so that this thing, right, we want to be consistent with normal practice in algebraic geometry where O of n is the thing that has lots of sections. So this ring is sort of reasonably big. I should mention, note, this will come up again in a moment. I should have said this earlier, that the global sections of the curve are just QP. And from that, it's easy to deduce that the sections of O of minus n are 0. So so to speak, the constant functions on the curve are just QP, which kind of makes sense because it's not obvious how you would write down any other constant functions, but in fact you have to check something. Because, right, I mean the definition of these rings involves some completion, and so it's not clear that you can, the elements of these rings that I use to build these do not have simple power series representations. So it takes some care to check statements like this, but they're both true. Yeah, so this gives you some, so this thing in turn is some large QP vector space, and that gives you a reasonably large graded ring here, and the proj of that is what's called XF. And so I told you last time that these things are closely related in the style of an analytification, that coherent sheaves on XF are equivalent as a category via pullback to coherent sheaves on the adic version. And so that will also be true for vector bundles. locally free coherent sheaves. Definitely not equal. So mostly I'm going to focus on the vector bundles in what I'm about to say. Because these spaces are one-dimensional, it turns out that every coherent sheaf can be resolved by a two-term resolution of vector bundles. So, right, you know of O of 1 is ample, so you can write down some direct sum of copies of O of something that surjects onto any given sheaf, and then the kernel will automatically be a vector bundle. So the projective dimension of it is at most 1. Okay. So that's the picture we have. We have these two spaces that have essentially the same sheaf theory, and now I want to tell you about the vector bundles. And we'll see in the later lectures how the story of these vector bundles has all sorts of impacts throughout arithmetic geometry. Yes? Yes, it is a XFN is a quasi-compact adic space, right? Because right, I took this. Right, YF was not quasi-compact. It had this dimension which kind of looks like positive real numbers, but then I'm dividing that by multiplication by p, essentially. So I'm kind of, in terms of the homotopy types, I'm taking a contractible thing and then wrapping it to make a circle. So yeah, XFN is quasi-compact. XF, well, it's hard to say what it means that it's proper because it's not finite type over anything reasonable. It does. I guess it does satisfy the evaluative criterion, but you know, it's not finite type. YF is what's the right way to think about YF? YF is a little bit like. So there's a good analogy. If you try to do the equal characteristic version of this, where instead of p you take something in positive characteristic, which is just a series variable. Then, if I remember correctly, YF acts something like, YF behaves something like sort of P1 minus 0 infinity, so GM, basically. And this is like taking the coordinate to its pth power or something. So, so that's sort of the picture. Is you have this, the analytic GM is like P1 minus 2 points, so that's not quasi-compact. But then you kind of wrap it, or you do this quotient thing to kind of make you take some annulus and then you glue the two ends together, and now you have something that makes it sound like a tate-elliptic curve or something, which is now compact. Okay. So let me now give you a key definition, which is not original to this subject. So let V be a vector bundle. So in light of Gaga, I don't have to tell you whether I'm talking about XF or XFN, so maybe I'll just say vector bundle, and I'll mean either of those things. They're equivalent concepts. So I'm going to associate to V several numerical invariants. One is the rank. So rank is a locally constant function, but these spaces are connected. So the rank is a unique non-negative integer. So this is the rank is always some well-defined non-negative integer. I get the vector bundle. So there's degree of V. So this is going to be by definition. Well, for a line bundle, I have a degree function coming from the degree function of divisors. So what I'm going to do is I'm just going to take the top exterior power of V, so-called determinant. So I might call this the determinant of V also. So the determinant of V is its top exterior power. That's a line bundle. So I take the degree of that via the map that we constructed from the Picard group to the integers using the fact that principal divisors have degree 0. So it's just the, given that you know what degrees of closed points are, this is, so it's convenient to make this definition on the algebraic side, so I can talk about degrees in terms of closed points. You can also interpret the degree in terms of what happens when you pull back to here, but let me not say that. Okay, so this is the degree is some integer, of course, and the degree of O of n is n, as I had mentioned last time. And then the key invariant that I want to add to the picture is what's called the slope, which is denoted mu for reasons that I don't remember, but maybe somebody who knows more geometric invariant theory can remind me. This is just degree divided by rank. And this, of course, is only defined if V is non-zero. The slope of the zero bundle is undefined. Okay. So this, right, so in classical theory of vector bundles on a curve or a Riemann surface, right, this thing is, the degree is telling you something about how many linearly independent sections you can write down. And so the slope is somehow, some kind of weighted count of this because, of course, if you take the direct sum of two bundles, or even an extension of two bundles, then the degrees will add. So this is like some kind of average number of sections weighted by the rank. Now, in this context, these spaces are not finite dimensional, right? It's not like for P, if we were doing this for ordinary P1 in algebraic geometry, this would be a space of dimension n plus 1, but here, there is a dimension theory for what are called Banach-Kolmez spaces in which this thing has degree something like n plus 1, but I don't want to get into that. Just suffice it to say that this thing gets bigger and bigger as n gets larger, and the slope is somehow measuring, in some sense, how many sections the bundle has. Yeah, it's somehow quantified, it's some very crude measure of how many sections the bundle has. You should think more that it's set up to be we're following a formal analogy with vector bundles on curves, where this slope is more more closely related to numbers of sections. That's correct. So XF is Noetherian or regular of dimension 1, and it has every principal divisor has degree 0, so it's like a complete curve. So we're expecting that the theory of vector bundles will be a little bit like vector bundles on a complete curve. And so that's why we're setting up the notation in anticipation of that. And so, so the key definition here now is, well, this is one key definition. And once you've made this definition, it's natural to make this one. For V, so if V is non-zero, I'll say that V is stable or semi-stable if for all proper non-zero subbundles, proper meaning like it's not the whole thing, not proper in the sense of a proper morphism. So stable is going to be characterized by the property that the slope of V is strictly bigger than any of these subbundles, and semi-stable is the boundary case being allowed. So for example, the sum of two stable things is not going to be stable, but it has a chance to be semi-stable, and in fact it is. So I should apologize for the fact that I'm using the word semi-stable in ostensibly a different way than we used it earlier, but in fact, these two uses of right, we talked about semi-stable Galois representations, but these both come from the same place. They both come from geometric invariant theory. So we're kind of stuck with the fact that the same word, the same original meaning somehow wound its way through mathematics in two different ways, and these two uses are meeting up in this story. You know, some might argue that that's a feature, not a bug, but it's kind of neat that this concept has percolated. This concept of stable orbits in groups somehow has filtered through mathematics in multiple ways. But okay, so we have this notion. So I'm mostly going to talk about the semi-stable ones, but so a key example is, and if this example were not valid, then this whole theory would fall apart. But O of n is stable for all n. So this is, in fact, maybe I should really say any line bundle is stable. Any line bundle is stable. Well, how is there any content in that statement? Well, right, a line bundle can have subbundles which are still of rank 1. I didn't insist that the quotient be a line bundle. So inside a line bundle, you have subbundles potentially. So for example, O of n contains O of n minus 1 in various ways. But of course, if you're looking at this comparison, you can, right, if you're comparing the slopes of these two things, you can twist by some other line bundle, and you'll get another comparison, and you won't change the difference between the slopes. So in fact, this is equivalent to saying that O itself is stable. Right, because if you have an inclusion of two line bundles, well, you can twist by the dual of this one so that you're in the situation where you're just looking at subbundles of O. And then the fact that O is stable essentially is a consequence of this. Yeah, I should say, well, so obviously if I have, you asking about direct, like extensions or tensor products? Yeah, so for direct sums or extensions, so the rank of v plus v prime obviously is the sum. The degree is obviously also the sum, because, right, the exterior power of a direct sum, the top exterior power of a direct sum is the tensor product of the top exterior powers of these things. And so what does that say about the slope? Well, it doesn't directly say anything because you have two fractions and you're adding the numerators and denominators. Obviously, it'll be somewhere in between the two with equality if and only if the two are equal, but otherwise, it's not so obvious. Yeah, it's whatever the thing is called, the mediant of those two fractions. But you have to keep them, right, you have to write the fractions not in lowest terms. You have to write them in these terms. Because they're. Okay, so I can give you some, so this is not a very interesting example of something stable, but I guess I can make interesting examples of semi-stable things out of it. So this implies, so from this it's not so hard to deduce that if you take some direct sum of copies of O of n, this is going to be semi-stable in general. It can only be stable if m equals 1, but in general it has a chance to be semi-stable, and it turns out it is. There are slightly more interesting examples of stable bundles. I'll come to those in a moment when we start talking about the classification. But first, I want to point out that this basically is enough to deduce the following, which we saw in another guise yesterday. So this is a proposition definition, or lemma definition, if you want. So every vector bundle has a unique filtration the length is whatever it has to be. I won't tell you in advance what the length is. So this filtration is characterized by two properties. One, each of these, so first of all, each quotient of successive terms is actually a vector bundle. So there's no, so there's none of this business of taking a line bundle inside another line bundle. The rank actually has to keep increasing, and there's no torsion. So this quotient is a vector bundle. First of all, it's a vector bundle, and second of all, it's semi-stable. Subslope, which I'll call mu I, and this is the part, so this is not at all, so there are many filtrations like this, but there's only one that has the property that the slopes go in decreasing order. So you can, in fact, you can, basically the way you prove something like this is you first figure out what the first term has to be. So the first term is, it's called the destabilizing subbundle. So you basically look for the, I think V1 is the largest, it has the largest slope among all subbundles, and among the ones of that slope, it's the biggest one by rank. And so you have to prove that such a thing exists. But this is a relatively formal thing to do once you know this. And so this is what's called the harder Narasimha filtration. This is not, so there is no easier Narasimha filtration. This is Günther harder. I got tangled up with this last time, so. So yeah, so once you kind of have the basic properties of the situation, it's a relatively formal construction to construct this thing. And so but you do have to do you have to prove something in order to show this exists. So that's why I didn't write it as a definition. It's formal, but it's not entirely trivial. You can find this argument in various places. Written in quite an abstract form. So for example, in the book of Farc-Fontaine, they give a version of this, they sort of axiomatize what it means for an abstract complete curve to have filtrations on its vector bundles. And in my Arizona notes, I also talk about this. Yves Andre has a nice paper about slope filtrations where he also gives a really general formulation of this kind of construction, right? As we saw in Denis' lecture yesterday, right? You can have this kind of story even when you're not a priori talking about vector bundles, right? I mean, filtered phi modules also present some story like this. So and there are even examples involving things like Euclidean lattices. The notion of these filtrations can occur in quite generality. Yeah, basically the main point is to show that there is that the set of all slopes of subbundles is bounded above, and therefore has a largest element. It's formal once you know this, I think is the, I mean, it depends how you want to quantify it. So, as I said, in Farc-Fontaine, they talk about an abstract complete curve, and in that context, you also have something like this. Because again, this just comes down to the fact that the sections form a field. The sections of the structure sheet form a field. Yeah. So there's not so much content hidden in here, but there is something you have to prove. But once you've done this, now you can start talking about these filtrations. I should make a comment about, just for orientation purposes, one consequence of this is that if V and V prime are semi-stable, and so if you have semi-stable things and mu of V is bigger than mu of V prime, then there's no homomorphism. There are no morphisms from V to V prime other than the 0, 1. So for example, there are no morphisms from O to O of minus 1. That's what I said here. But it's that statement sort of applies to arbitrary semi-stable things. Oh, and I should caution. So it's very tempting to believe that you can say something about tensor products because, right, the degree of a tensor product is, well, you can write it, it's some expression you can write down explicitly in terms of the degrees of these things. It's like, it involves that you take the degrees of the two factors and then you raise them to some powers. So there's it's easy to calculate the degree of a tensor product, but it is not formal to see that the tensor product of two semi-stable things is semi-stable. That is not a formal consequence of just the axioms. And in fact, to convince you that it's not formal, I can point out that this is true in classical vector bundle theory. This is true in characteristic 0 and false in characteristic P. So in the classical vector bundle theory, this is true in characteristic 0 and false in characteristic P. So the truth of this in characteristic 0 follows from a theorem that I'm going to mention later by Narasimha and Chaudhuri, because we have an analog of that. And the characteristic P, the failure in characteristic P is due to Giesecker. And it was, I think, quite disorienting at the time that I mean, now we're kind of used to it, but I think this was. Which one? This? Yes, so this is, right, so, well, for filtered phi modules, it's faulty Sutaro. Let me not, maybe that, yeah. Yeah, for the context of filtered phi modules, that it is true, and that's, yeah, it was shown by Totaro. But yeah, it takes some, it's not a formal consequence of the setup, is the point, because there are setups that look very similar where that property can fail, most notably vector bundles on an algebraic curve in characteristic P. Okay, so that was the caution. Yes, I'll come back to this in a moment. Yeah, so it is true in this case. It is true, but, and in some sense it's almost equivalent to the classification, but let me state the classification first, and then it will, from the classification, it will certainly follow. Okay, so what do I need to do? Oh, I need to define polygons. So there's a Newton polygon associated to this construction, which I'll call the Hard-Narasimhan polygon, is the Newton polygon. So how do you make Newton polygons in general? Well, a Newton polygon generally corresponds to some collection of slopes. Well, I've conveniently called these things slopes to set up that terminology. I don't get credit for that, but so there is a polygon that you draw. So all I have to do is tell you what the multiplicity is of a given slope. So the multiplicity of mu I as a slope is going to be just the rank of that quotient. And so these multiplicities add up to the rank of the bundle. So note, if I can also associate such a polygon to any filtration with semi-stable quotients. And so these are, I guess we're using convex Newton polygons. So in my Arizona notes, for some reason I had to use concave Newton polygons, but let's say we're using, I think in the other lectures we've been using convex Newton polygons. They curve up. So if I use convex Newton polygons, then if I define a polygon with respect to some other filtration, then this lies below, on or below, the canonical one with the same endpoints. For example, and this example will be crucial in the proof of the classification, so I mention it here, one can have, and of course it's also crucial for p-divisible groups, maybe we'll see that, one can have a sequence, one can have a short exact sequence where the sub is, which way do I want to do this? Let's say O minus 1 over n. So you could have a sequence like this. So this is not of the right form because, oh shoot, I haven't told you what this is. Well, you could have, let me just do it with 1 and minus 1 then. So you could have something like this. So rank 2, the minus 1 is a sub, so that's the wrong way around. But this does have semi-stable quotients. But where V actually is semi-stable of degree 0. So in fact, it can be 2 copies of the structure. Well, let's write it this way. So you can have a filtration like this, where the thing in the middle, which is not split, and the thing in the middle actually looks like 2 copies of O. And this is sort of a fundamental example.
To make it convex or concave,
Yes?
you can do one of 2 things. Either start with mu n and mu1, or take minus mu1 minus mu2 up to minus mu n.
Yes.
Which is the convention?
I am taking, I start with the small, right? I put the small on the left.
No, you do not take it off.
Yeah, so in order for this thing to be true, right? So in this example, I'm thinking of, well, I think in this example, the 2 coincide. The harder Narasimha polygon is the flat one of length 2. So the HN polygon is up here, but the other one goes down by 1 and then up by 1. Yeah, in this example, those 2 actually coincide, but you know, once I had the 1 over n here, then there's 2 different choices. I mean, I think those are just mirror reflections of each other, so it won't affect anything I'm saying, but of course you don't want to mix them up in practice. Okay. So now, in order to state the classification, let me define the O of a rational number that I was about to use. So say R over S is a rational number in lowest terms. So that means that the GCD of, so R and S are integers. S is positive, and the GCD is 1, right? A rational number has a unique representation in that form. So there's exactly one example of this construction for each rational. So O of R over S is by definition the vector bundle of, well, I'm first going to define it on the analytic side. So it's going to have rank S. That's a positive integer, so that makes sense. So if I pull it back to YF, it's again, just like O of n, well, on Y of F, this is going to be trivial. This is going to be free on generators E1 through ES, satisfying. And so the thing I have to tell you is how the phi action operates on these generators. So it's going to be a shift until I get to the end, and then the shift is going to be twisted by p to the minus r. So this should look familiar. This is the building, this is basically the building block object in the Dieudonné-Manin classification that we saw yesterday, I think it was. You can also think of this as, well, you can define another curve, xf to the s, where instead of dividing by Frobenius, you divide by the s power of Frobenius. And then this is like taking O of r on that guy and pushing it down by the degree s map. But I won't write that on the board. I just mentioned that this is, in Farb Fund 10, they like to present it that way. But okay, so I now have this vector bundle. So lemma, this is stable of, it's obviously degree s if slope r over s. So if you do this in terms of the s-fold covering, then this just comes down to the fact that on that covering curve, O of r as again slope r. Yes, stable. Yes, stable implies, right? I can, I guess, point to this. So remember the discussion we had about a direct sum. So if you have, if something was, right, so that if you have a direct sum or even extension, then the slope is some sort of weighted average of the two other slopes. So, stable actually implies irreducible for that reason. All right. S, which on YF, if you pull back to YF, so you pull back to the Frobenius cover, so there it's a trivial vector underlying vector bundle, but it has a non-trivial phi equivariance given by this formula. And it's stable, which implies irreducible. I'm sorry? Semi-stable implies, no, it doesn't. Direct sum of, I have the counterexample on the board. But stable implies irreducible because of the behavior of slopes under an extension. Okay. So now I come to the main theorem of this part of the talk, which is the classification of vector bundles. When F is algebraically closed. So suppose F is algebraically closed. You'll see in a moment something that can happen when F is not algebraically closed. Things will look a little bit different. So part one of the statement is a vector bundle V of slope mu, say, actually I'll write it as R over S, is stable if and only if it's isomorphic in some way to OR over S. Oh, sorry, you're right. Yes. Yes, right, I have that example over there. So let's, it's, sorry. Yeah, the example, I still have the example on the board. Something's stable, or semi-stable. Well, that one is stable. I could make a stable example like that too. And two is that every vector bundle splits, although not uniquely, as a direct sum of stable bundles. So every vector bundle can be written as a sum of various O of R of S's. And I'm writing mu as R over S for consistency with, just to emphasize So if a vector bundle has slope mu, the only way it can be stable is for it to be the unique representative in this family of that slope. So this is the classification of the stable vector bundles, in other words. There's one for every possible slope and nothing else, in the case where F is algebraically closed. Yes? That's right. No, I want it, so remember how I defined O of 1. I defined O of 1, right? If you take R of S equals 1, this reduces to my definition of O of 1, and there I had a p to the minus 1. And I wanted that because I wanted the sections of O of 1 to be, non-trivial. Yes, so it's the opposite convention from classical Jön-Neymaanian theory. But this convention, in this language, this convention is obviously the one that makes sense because O of 1 is supposed to have the sections. Yes, it is the opposite convention from, so, yeah, so, and this gets to a point that in this form, this is one of the main theorems in the book of Fargue and Fontaine, but it also follows from what you might call the classification of Jön-Ney modules. There's an analog of the Jön-Neymaanian classification for the phi equivariant vector bundles on YF, which is of course another way to say this, and well, modulo translating notation and this sort of thing, this is an older result of mine. So, right, the work of Fargue and Fontaine, as I understand it from Kolmez's introduction, one of the things they were trying to do was trying to kind of arrive at this classification in a different way, in this more geometric way, and indeed they give an independent proof of it. Right, it sort of meets, but it meets up with this older result of mine, which is stated using the usual convention from Jön-Neymaanian, where I have the slopes going the other way. Phi equivariant vector bundles on YF. So remember, right, vector bundles on here are the same as equivariant vector bundles on the cover. So of course, my statement is not stated in terms of vector bundles because I didn't have a curve at the time. This thing is a quasi-Stein space, so the vector bundles are actually, the vector bundles here are basically free modules. So these are phi modules over the ring of global sections of YF, essentially. This is sometimes called the classification of Jön-Ney modules over the robo ring. Okay, corollary. So F is F bar. So I'm not going to say much about the proof of this. I might make one or two comments, but it's but I want to state this corollary first. V is semi-stable of some slope mu if and only if V is isomorphic to some direct sum of copies of O of mu. So we also know what the semi-stable things are, but this is not a unique decomposition either. But there's not so much ambiguity in it because the ambiguity involves sections of the structure sheaf which are just QP. So say again? Yes. Yeah. So this is like what happens for like P1. Yeah, so this is, Fargue and Fontaine like to say that the curve kind of looks like it has genus 0 in various ways. So yeah, by the way, this implies the stability under tensor product. This implies the preservation of semi-stability under the tensor product using the fact that O of mu1 tensor O of mu2 is isomorphic to some number of copies of O of mu1 plus mu2, where you have to choose it to make the ranks work out. But you can write this isomorphism down. This is a fun exercise to write this isomorphism down explicitly. Yes, when when f equals f bar, let's say. But right, so in principle, you're saying this implies the preservation of semi-stability in the tensor when f equals f bar. Yes, but it also implies that when f is not f bar, because if you start with something semi-stable and let's see. Well, you have to check something. You have to check that something semi-stable stays semi-stable when you pull it back to f bar. But that part is not hard to prove. And then you take the tensor product and you get something which is semi-stable over f bar, but then it came from something in f. And so the direction that's easy is if something is on f and it becomes semi-stable over f bar, then it was already semi-stable over f because you have fewer subbundles over f. But you also have to check the other direction. Yes? No, but there's the following thing. So of course, the hard Narasimha infiltration is canonical. Yeah, maybe that's what you mean. Yeah, so maybe I should mention, I should maybe state this as a corollary. The HN filtration is stable under base extension. I think this is what you're maybe asking about.
No, I meant local filtration, like that vector bundle's not that far constant for f bar. Go on.
Yes. Yes, that's true. Yes, you can do Galois descent for basically any, from f to f bar, for example. And that actually that is used in the following statement, which is one of the key corollaries. So this is the analog of Narasimha/Chaudhuri. Let me just say it. So for general f, there is a really short on time here. There's equivalence categories from vector bundles on xf, which are semi-stable of degree 0. And, the category of continuous representations of GF on finite dimensional QP vector spaces, so rep QP of GF. Given by vector bundle goes to, you go to the completed algebraic closure of f bar hat. So you base extend to there. There, it's still semi-stable of slope 0, so it becomes isomorphic to just a bunch of copies of O. And so when you take global sections, you get a finite dimensional QP vector space, and which remembers how GF acts on it because of the base extension. And then to go the other way uses exactly the descent theorem that we just discussed. Because from this way, you get the semi-stable degree 0 thing with Galois action, and then that descends. So these are on XF. Yeah. Sorry? These are finite. Well, they're finite dimensional QP vector spaces. No, but the image can be the image can be large, going from F all the way to F bar. So this, I guess I should, since people asked about the Picard group last time, so this tells me I can use this to compute the Picard group, because if I have a line bundle, well, I can always twist it by O of n to get something of degree 0. It's automatically stable in that case, and then what's left over? Well, it's just the one-dimensional things here. So it's like the continuous homomorphisms from GF to QP star, QP times. So now you know what the Picard group of the curve is. It just came out of this. I mean, you could also calculate this more directly, but you don't really need to. Okay, right, so I mentioned this is analogous to the theorem of Narasimha and Chaudhuri, right? That theorem says if you have a compact Riemann surface and you look at, say, stable vector bundles of degree 0, those correspond to irreducible unitary representations of the fundamental group. So somehow this GF is acting like the fundamental group, which makes sense because you can prove that if you take the curve over F, you take the curve for an algebraically closed field, and well, it has coefficients over QP, so you extend the coefficients to CP or something. So we're talking about a geometric pi1, then that thing is geometrically simply connected. That's due to Weinstein in some form, and then Farg in a stronger form. Which one? The thing I just said? This thing? This is a corollary of the theorem, of the classification, because you use the classification over F bar hat, to say that this is a finite dimensional QP vector space, and that you can recover the bundle, the semi-stable bundle from this.
One should be able to say what it means for representation to be crystalline in terms of vector.
Yeah, I'm not going to try to do that right now. Maybe, I don't know if that will come up later. But yeah, you can translate properties of, right, if you have a representation of GK where K is finite over QP, well, you can't directly apply this, but once you go to say, the cyclotomic extension, you can apply this and then keep track of the gamma to take you back down. And then you can talk about various properties in terms of this vector bundle plus that extra descent data. Sorry. Keep order. Yes, F has to be perfectoid here. I mean, right, you take QP cyclotomic, say, and then you tilt it, and then you take that to be the F. Sorry, let me get this question down.
The perfectoid representation comes from the fact that a priori
yes, so I'm using the fact that G, you mean when in the QP situation? Like if I take QP cyclotomic, yes, the Galois group of QP cyclotomic over QP will then still act on the tilt of QP cyclotomic. It just won't look like a Galois group anymore, but it will still act on that field. F is the field of characteristic speed, so F would be the tilt. So you could apply this, F being, you take QP cyclotomic, and then you tilt it. But of course, the tilt preserves the Galois groups. So this thing still, and it's functorial, so this thing still has an action of gal of QP cyclotomic over QP, which is isomorphic to ZP cross, and this is what's the thing we call gamma. Yes. They're the same. They're canonically no, I mean, no, naturally I think I have an action of the, I mean, this is a philosophical point. You have an action of this group on here. You have a natural action of that because of the action of GF on this field. Okay. Right, okay. So I was planning to say something about the proof, but maybe I won't. Maybe I'll just say that, yeah, maybe I won't say that at all. I want to take just a couple of minutes at the end to say something about the relative case so that I can kind of pick up on that theme when I talk on Monday next week. A quick word about the relative case. So maybe I'll just write one board full of these comments and then, so there is an analog of well, there is an analog of both of these constructions. both the analytic and the schematic construction have analogs when star is a, well, you could put a perfectoid ring. So you could, or, well, let me start with the case of a perfectoid ring. Yes, a perfectoid ring of characteristic P. If you start with something at characteristic 0, well, I'll say about untilts. So there is an analog of this picture over a base perfectoid ring. The catch is that it's no longer Noetherian. Nothing in the picture is Noetherian anymore. So first of all, you have to be careful to understand why are these things, why do you get a genuine adic space when it's not sheafy? It turns out you can show it's stably uniform, but let me not go into that. Also, you have to restrict yourself to talking about vector bundles unless you're sufficiently careful. In my talk next week, I'll say a little bit about some situation where you can talk about other coherent sheaves, but mostly you should just think about vector bundles in this picture. Yeah, so given, so any untilt of the base ring defines a section of, so when you have, say, R as a perfectoid ring, so if you have a perfectoid pair here, you have a morphism of, well, I'm going to write this with a dashed arrow. So this, as a topological space, the relative construction gives you a topological space mapping to this thing. This is only a morphism of topological spaces. This does not have any structural meaning at the level of structure sheaves because this is characteristic P and this is not characteristic P. So there can't be a morphism like this, but there can be a morphism like this. And so whenever you have an untilt, that actually kind of gives you a, well, it doesn't quite give you a, well, what I should say is, if you pick an untilt of, say, AA plus is an untilt of RR plus, then these two spaces are homeomorphic. And now there is a section corresponding to this untilt. In fact, it's a closed immersion, whatever that means. So this structural morphism has section, sort of every time you pick an untilt, you get you get a section, which you can even make sense of by changing the base, by changing the structure sheaf on the base. So this is the sense in which this thing is like a moduli of untilts of this thing. Or rather, really the right way to say that is that the stack of these curves over all perfectoids is the moduli space of untilting. Yeah, so there's a theory of vector bundles on these things. So there's a gaga here. So gaga for vector bundles. So this is mostly out of my long asterisk volume with Liu. So you have gaga for vector bundles in this context. You would have it for coherent sheaves if you could deal with coherent sheaves, but that's a little bit hard to say, so I won't try. So you have a gaga in this situation. What else do you have? XR is, I mean, it's not Noetherian. So there's no way to talk about coherent sheaves without being super careful. So yeah, but vector bundles still work because, right, somehow the flatness is all in the modules. So vector bundles work even on non-Noetherian things quite nicely. So you can do gaga for vector bundles. You can talk about, so if you have a vector bundle on a relative curve, you can talk about the variation of the HN polygon as a function of the base. So, right, if you have so say you have a picture, say you have this picture of relative curves over some base. So if you have a vector bundle on this total space, you can restrict it to any fiber and you'll get some polygon. And so you can ask, well, how do these polygons behave? Well, you would expect them to have a semi-continuity property, just like for an ordinary vector bundle theory. And so Rochwan and I proved that that semi-continuity property does hold. You know, and then when all fibers are semi-stable of slope 0, these things, you expect them to correspond to something like Galois representations. They correspond to the analog in this picture are étale local systems. Essentially representations of the fundamental group of the base. So that's what plays the role of the Galois. So there is this whole relative picture, which works quite nicely in concert with the absolute picture. And there are a couple of applications of this. One that I won't talk about is in the construction of moduli spaces of these vector bundles. For this, you have to globalize. So instead of perfectoid rings, you think about perfectoid spaces, and then you think about certain stacks on the category of perfectoid spaces, particularly things called diamonds. So that's one direction you can go with this. The other, which is what I am going to talk about on Monday, is you can use this kind of construction to study the cohomology of local systems on rigid analytic spaces by kind of making suitable coverings of them by perfectoid spaces, keeping track of descent data, like in the definition of a phi gamma module, something like the gamma, and using this geometric picture as the kind of the place where the right. So right, it's sort of generalization of the passage between phi gamma modules and vector bundles, which I think we will talk about next. Will that come up in the next lecture? Well, maybe not in exact. I mean, something like it will come up in the next lectures. All right, so I should stop there. I'm out of time.
This board is gamma X F. What are the indicators?
So this thing looks like, right, this thing is abstractly some powers, some completed perfect closure of a power series field. The invariants are just FP. So the invariants are somehow really small, which befits the fact that we've taken a construction where there's a Galois group of one thing over another, and we've done something where that tilts the upstairs, but there's no way to tilt QP. So yeah, the group action here is something that does not have any reasonable. I mean, there's no reason to expect that the action of this ZP star on here has any reasonable invariant theory, and it doesn't. That's right. That's what that PF was standing for, perfect closure. Yes. So you have to make this perfect and then complete it. Yeah, in this picture, you get a scheme. So when you take a perfectoid ring, you can get a scheme and an adic space. Now, in the long run, what you're supposed to really use is, you're really supposed to use the adic space, because you're supposed to then globalize from perfectoid rings to perfectoid spaces. And in that context, there's no scheme anymore. There's only the adic space construction, the glues. So you do have a scheme here because you have essentially because this thing is a ring, but that's not the interpretation that one uses when one passes to perfectoid spaces. That interpretation really has to be done in the world of adic spaces. Yeah, so one can talk about these relative Farc-Fontaine curves over a perfectoid space, or even some stack on the category of perfectoid spaces. So for example, Scholze has to use this in his Berkeley lecture series. Yeah, the fibers are, right, so there's a sort of compatibility of this construction with base change. So if you base change to a perfectoid field, you get back one of those things that you had earlier. But somehow the failure of the Noetherian property comes from the fact that the base is, the base, it's not, in some sense, is this ring R, which is heavily non-Noetherian. So.